Hello everyone. So today let's solve the problem weird journey, right? So this was asked in the code forces around 407 for the division 2. So you can just go through the question. It's easier to understand. This is very easy. I'll just summarize the question so that it will be easier for us to solve the problem. Let's see what the question states here. Just one second. Just give me a second here. Yeah. So we are given n cities here, right? So we are given n cities and m directional roads and m this one bidirectional roads, right? A good path uses exactly a good path. I'll just mention this one as GP. A good path uses exactly m minus 2 roads. Yeah, this is very important. A good path uses exactly m minus 2 roads twice, m minus 2 roads twice, and remaining 2 roads exactly once. And remaining 2 roads, I'll just write it here, are remaining 2 roads exactly once. Exactly once, right? Roads can be self loops or connect, or it can connect different cities, right? So what we need to do here, what is our main task? We have to count the number of different good paths. We have to count number of different paths, good paths basically, number of good paths, right? So just remember this one. So let me read the question loudly. Just listen to this carefully, man. Yeah. So we are given n cities and m bidirectional roads, right? A good path uses exactly m minus 2 roads twice and the remaining 2 roads exactly once and the remaining 2 roads exactly once. So roads can be self loops or connect different cities. What we need to do, we have to count the number of different good paths. We have to count the number of different good paths, right? So that's what we need to do. When it comes to this one, see here, output. So we have been given n and m here. So this one number of nodes actually, and m we have been given 4 here, right? So see here, number of nodes is 5, 1, 2, 3, 4, 5 we have. By looking at it, you can clearly see here, right? So the graph you can just go with in this way actually. One, two, uh, oh, this one we have four, 1, 2, 2, 1, 2, 3 actually, 1, 2, 4, 1, 2, 5. Oh, this one is the center then. One is the center then. Yeah, for every node actually. Yeah, this is fine. The output that we need to get here is 6. Yep. The output that we need to get here is 6, meaning the number of different good paths are 6 basically. The same goes with the example 2 as well and the example 3 as well. Yeah, let me delete this one. Man. Now we have the understanding of the question. It's easy. Let's do one thing. Let's quickly discuss the approach followed by the this one. What do we call? Complexities, and then let's write the code. As usual, let's discuss the approach first. So here I have considered the same first example that they have given in the question, right? So we have already discussed this one and then the edges as well. So next, the output that we need to get here is 6. So one thing here I want to tell you is we will be going with the Euler tour technique as well as the this one DSU. Along with the Euler-Tour technique, we'll be going with a DSU. So we have discussed the Euler-Tour technique algorithm within the tree-based algorithm. If you don't know, you can just go through the playlist tree-based algorithms and you can just check the Euler-Tour technique all go there and you can just come back, right? So you will have the idea what we will be doing. Else, if you have to blindly follow certain things, right? So don't do that. I insist you to, if you don't know what Euler technique is, or Euler tool technique is, just go, just open the playlist, this one tree based algorithms, this one playlist, just see, just you can just watch the video, you'll have the idea what Euler tool technique is, then you can come back to the problem, you'll understand this one crystal clear. And all these days we have been solving the problems on DSU as well. Disjoint set union you have to know at this point of time, right? So we will be making use of Euler tool technique as well as the DSU, disjoint set union, to solve this particular problem, right? So let's see how can we solve this particular problem, right? So we'll be making use of the Euler-2 technique as well as the DSU or the union find, right? So let's move on with a step-by-step explanation. So this is the input that they have given and this is the graph actually. Yeah, this is the graph actually. You can just have a look into it. 1 to 2, 1 to 3, 1 to 4, 1 to 5, right? So this is the center basically. Yeah, now the graph forms a star centered at 1 basically. Yeah, it is the star centered, right? From this one node 1 itself, we are connecting all other nodes 2, 4, 3 and 5, 2, 3, 4 and 5 basically, right? So the graph forms a star centered at 1. The second point here is degree of 1 is 4, 2, 3, 4 and 5, right? Degree of others is quite obviously 1, right? So this is fine, I believe, easy. Good paths involve choosing any two edges to transform to to traverse exactly once, right? Good paths involve choosing any two edges to traverse exactly once. From one, we can just consider this one 4 comma 2, right? 4 comma 2 4 and 2 2, right? So when we sum up this one, we will get 6 ways actually. We can choose any edges, two edges among 4, right? So we have edge 2 3, this one, sorry, 1 to 2 1 to 3, edge 1 to 2, edge 1 to 3, edge 1 to 4, and edge 1 to 5, right? I have shown you the graph previously. This one we can choose any two adjustment, this one as well, right? So this one we will get this one 8 basically. So this one we can choose any two edges actually. We'll be choosing first two, so your 4 comma 2. So we will be going we'll be getting 6 ways, right? So here self loops contribute separately. Choose two loops or one loop plus one other edge, right? So we can choose either two loops or one loop plus one other edge, right? So this is fine, I believe. So we have to ensure all the edges are in the same connected component. We have to ensure all the edges are in the same connected component, right? It is connected to the same parent or same representative in simple terms, right? So if you know the DSU algo using the DSU, right? So if you don't know the DSU algorithm still, you can just go through the DSU algorithm on the this one graph algorithms playlist, right? So we are at the end. Today we'll be finishing this one, graph-based algorithms as well. So I can just go through the DSU algorithm from there, right? If you don't know. So now the final output that we got here is 6, right? 6, which is equivalent to the output that they have mentioned for the example 1 within the question. So our approach works absolutely correct, right? Our approach works absolutely correct. So what is the idea here? Um, so we will count the pairs of the edges that can be traversed once, either two edges connected to the same vertex, two edges connected to the same vertex, or the two self loops. We have already discussed this one, and one self loop plus one normal edge. We have connected this one. We have discussed this one, right? Already. So now we have complete idea, right? We are completely familiar with the approach. So let's move on with the complexities part. So what will be the time complexity here? The time complexity would lead to big of n plus m. So why it is n plus m? So we will be going with the DSU operations here, right? We'll be making use of the DSU. Plus we will be going with the degree counting here. We'll be going with the degree counting as well. Also, we will be going with the loop checking, right? Degree counting, Euler's pair, this one, Euler 2 technique, and loop checking as well. Loop checking as well, right? So overall time complexity would lead to big of n plus m. What would be the space complexity? Space complexity would lead to big of n, because we'll be making use of the arrays for the parent, degree, as well as the has edge. Has edge is nothing but this one for the Euler 2, right? So Eulerian pairs we can call in simple terms, right? So the space complexity, the time complexity, and the space complexity for the code that we'll be writing in the future would be big of n plus m and big of n respectively, right? So now, as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code. So let's start writing the code. I'll just come here. We'll be making use of the fast input and the input. So fast input and the output. So let's import input output package. Yeah. Now we'll be making use of the this one as well, different utilities as well. So I'll just go with the let's import the utility package as well. So I'll just go with public class main. This is fine. So within the main method, let's do one thing. Uh, let's go with the maximum number of vertices first. Yeah. So I'll just go with static. So let me initialize to the, and so this one will be 1 followed by 5 zeros and 6. This is fine. Yeah. Now let's go with the DSU parent array, man. So I'll just go with static int. So let me go with parent equals new int of size n. This is fine. Yeah. Next, let's go with the degree of each vertex. So I'll just go with let me initialize the degree. So this one degree equals new int of n. Next, let's initialize has edge. Has edge is nothing but flag if it is the flag if vertex has at least one edge, right? So this one I can just initialize in this way. I'll just go with has edge. Yeah. So this one, let me go with new int of size and sorry. Yeah. Size and next let's go with a Euler loop. So I'll just go with the static int. So we are making use of the, as I've said, we'll be going with a Eulerian this one door technique, or Eulerian pairs actually in simple terms. So let me give here Euler loops, right? So let me initialize this one to 0. Yeah, now we are done with the initialization part. Now, as I have said, or as we had discussed earlier, so I said that we'll be making use of the disjoint set union, right? So let's go with the DSU find function with a path compression. So as usual, if you know the algo, we'll be going with a find, right? So I'll just go with in find to find the representative or the parent or the root with the along with the path compression actually. Yeah, I need the parameter x. So if x equals a parent here, parent of x actually, so then let's do one thing. Let's return x. This is fine. Then let's return this one. Parent of x is equal to let's go with the recursion here. Find of parent of x, right? So this one will be parent of x, right? So I'll just come out of this one entirely. Now let's go with the DSU union or the merge function, right? I'll just go with the static here, void. Let me go with merge. Let me go with two parameters, x and y. So this is fine, I believe. Yeah, x equals find of this one, x. Yep. Then y equals find of y. Yeah. Now if x not equal to y, then let me go with parent of x equals y. Yeah, this is fine, man. Let me come out of this one entirely. Let's do one thing. Let's go with the main method. Yeah, so I'll just go with main here. We remove this. Also, let me include here throws input output exception. Yeah, now yeah, within this main method, let's go with a this one first. Let's go with the buffered reader print writer. Also let's parse the this one integers. We have to read the first line, right? Let's make use of the string tokenizer. Also let's pass these two integers, right? Let me copy paste that one. Just give me a second here. Paste it over here. So this is purely related to the input output one. So I have just copy pasted this one, right? Yeah, let's move on with the further things. Yeah, as I've explained this one already. Now let's initialize the DSU. Let's move on with the iteration part. So this one is for int I equals 1, I less than or equal to n. Let me increment I here. So this is fine. Let me give here parent of I. Let me assign this one to I. And now let's check the connectivity. To check the connectivity, so I'll just go with int some vertex. Let me assign this one to the -1. Yeah. So now let's move on with a simple for loop, man. Yeah, iteration part. So this one will be int I equals 0, I less than m, I plus plus. Yep. Within the for loop, first let me go with the parts and let me assign this one to buffered reader dot read line. This is fine. Also, let me go with split here. Yep. Now let's go with int u and v. So I'll just make use of this one itself. I'll just change this one to u and v. The same thing we have to pass right here. It's this one node actually u and v, nodes u and v. It's u to v also I can consider nodes u and v. This is fine. So this one remains same. Parts of 0 we are passing this one passing to integers. This is fine. Now let's merge the vertices in DSU. We have already returned the helper method merge here. Let's make use of it, right? So how can we write this one? So I'll just come here after this. Let me give here merge of nodes u comma v. This is fine. Now let's go with has edge of u. Let me assign this one to has edge of v. Yeah, this one let me assign this one to 1. Right now let's do one thing. Let's go with some vertex. Let me assign this one to u as well. Right. So first let's go with the self proof, man. What if the value of u is equivalent to the value of v? Then we have to increment the Euler loop. So I'll just give here if u equals v, then let me go with the Euler loops, or let me increment the Euler loops, right? So else what we will do, else let me go with degree of U. Let me increment the this one degree. Also, we have to consider this one degree for the node B as well, right? So let me increment this one as well. Yeah, we are just going with a normal edge that increases the degree. So now let me come out of this one entirely. Now we are left with a few steps actually. Let's check if all the edges are in the same connected component or not. So for this one, I'll be making use of this one for loop. So this one int I equals 1, I less than or equal to n. So let me increment I here. So this is fine. So within the for loop, if uh, find of this one, let me go with some vertex not equal to find, not equal to find of I actually, find of I, and has edge of I. If it is equal to 1, then let me do one thing. I'll just go with the out dot println, sorry, out dot println. Let me pass 0 here, right? So this is fine, man. If it is disconnected, then we have no good path, right? So that is the reason I have passed 0 within the println. We are just displaying 0. This is fine. Next, let's give the this one. We have to flush the output, so I'll just give the out dot flush, or you can just make use of the close as well, out dot close. Then we have to exit, so let me give return here, right? So let me come out of this one entirely now. So we are left with this one. We have to consider the this one Eulerian pairs as well, right? So as I've said, so we are going with the Euler tour itself mainly. So I'll just go with Euler pairs here. Let me initialize this one to 0. Now let's do one thing. Let's count the pairs of self loops, right? If you know the algo. So I'll just go with here Euler pairs equals Euler space plus 1. Let me make use of L as we have made use of the long. So I'll just go with into, let me go with Euler loops into, so this one will be Euler loops minus 1 actually. Minus 1 by 2. So this is fine. The next step would be Euler pairs. This is fine. Euler pairs equals Euler plus plus 1. L the same thing into Euler loops. This is fine into this one M minus Euler loops. This is fine, I believe. Next step is we have to count the pairs of edges sharing a vertex. So I'll just go with the for loop here. So this one int I equals 1, I less than or equal to n. So let me go with I plus plus, right? So this is fine. Within the for loop, let me go with Euler pairs here. This one equals Euler plus plus 1L. So this is fine into degree of this one I, as well as into p of I minus 1 by 2. Yeah. Now let me come out of this one entirely. So this one will be out dot println. So println, let me pass the Euler pairs here. This is fine. So this is the final answer, as well as we are just displaying the final answer, right? By making use of out within the out dot println. Now let me give out dot flush actually. Yeah, or you can just go with the out dot close as well. So we are done with the coding part. So this is it for the code. So whatever we have discussed, this one, whatever we had discussed in the approach, the same thing we have articulated in the form of code. That's it. Yeah. Now, before checking the code with the different this one inputs or the examples, let me copy paste the signature starter template. Just give me a second here. So I'll just come here. Let me paste this one and let me come to the question. Let me copy this one. The output that we need to get here is 6. Let's check the same. Out.inteln it has become line number 67. Let's correct this one. Yeah, this one has to be this one println actually. Let me run this one again. Yeah, we are getting the output 6, which is absolutely correct. Next, let me copy this one. The output that we need to get here is 0. Let's check the same. So we are getting the 0. The final input, let me copy this. The output that we need to get here is 1. Let's check the same. So we are getting the correct output. Let me copy this one entirely and let me paste it over here. Let's wait for some time. What from D, right? Let's wait for some time. I hope this works for all the test cases, man. Let's see. Yeah, in the toast it is showing accepted, right? So the verdict that we got here is accepted. We have made use of this one, pure this one. What do we call Eulerian tour or Euler tour technique here, along with the DSU to solve this particular problem. DSU plus Euler tour, right? Eulerian pace we have made use of in simple terms. Yeah. Now I hope the solution part is completely clear, along with the approach and the complexities. For now, this is it. Thanks for watching, guys.